Module 1, Lesson 5. Lesson 5 outline contains open method techniques, specifically the secant method. I'll show you the derivation of its iterative formula, the initial conditions needed for this technique, and will evaluate a sample problem using secant method. Open methods are simply techniques that no longer restricted by the bracketing condition in selecting initial values for your iterative process. However, these techniques are no longer bounded by the bracketing condition, then as a result, some of these techniques eventually diverge. These methods are still applicable for both polynomial and transcendental functions. The secant method. Although the bisection method always converges, the speed of convergence is usually too slow for general use. A secant method is an improvement of the regular falsy method, which is better than your bisection method, and is applicable to both polynomial and transcendental equations. The secant method constructs an approximating straight line connecting two functions of your initial values, similar to that of your regular falsy method, to estimate your root value. The technique starts off by assuming two initial values that are labeled as x0 and x1, along with their respective functions fx0 and fx1. Note that the initial functions should only follow the condition that your fx0 taken from your initial value x0 should not be equivalent to your fx1, which is taken from your initial integer x1. This is a graphical depiction on how the particular technique works. You are first set up with an initial value x0, having a function fx0, and an initial value x1, having a function fx1. Since we are no longer bounded by the bracketing condition, you may select any two initial value you prefer, whether they are both negative or in this case, both positive. And then from which you connect the two functions using a straight line, and that straight line will eventually intersect your x-axis, thus giving you a new root estimate, x2. In order then to determine the iterative formula for your x2, just like your regular falsy, we then make use of this largest right triangle and apply ratio and proportion to a similar triangle, which is this yellow triangle. Or technically, we could also use that red triangle and apply ratio and proportion on this green triangle. Using then similar triangles to determine the iterative formula for your x2, you'd end up with this formula for your red triangle and your yellow triangle, ending up with an iterative formula like this when manipulated to evaluate x2. This other formula came from the red triangle and the green triangle using ratio and proportion, and if you try to manipulate solving for x2, you'd end up with this formula now for x2. Both formulas can be used, and both formulas are similar to your regular falsy, since both techniques make use of a secant line. So you may either use this iterative formula or this iterative formula. And then the whole process eventually continues on by using this substitution process. You disregard x0, you substitute your previous x1 to x0, and then substitute the computed x2 to x1 in order to compute for a new root estimate value x2. The process is then repeated until the terminating condition is satisfied, which is usually based from either an absolute error criteria or a relative error criteria precision type error. The second method does not have that bracketing property of your bisection method. And as mentioned, as a consequence, in some cases, this technique eventually diverges. However, when it does converge, it does generally faster than your bisection method. Let's try to evaluate this given example. Using secant method with a terminating condition of an absolute error less than or equal to 0.0001, let's try to establish again the root for this given function. And the usual concept is on your previous math that in order to establish the root for your given function, you simply equate it to 0. And then from which we start off the solution by assuming any two initial integer values as long as their functions are not equal. Hence, you could use this initial value with a function equal to -16 and this initial value 4 with a function equal to -6. Notice that both initial values have different functions. For your first iteration then, using this initial value 3 and 4, along with their functions -16 and -6, applying it onto your iterative formula, you would then end up with this respective solution with an x2 value now equal to 4.6. We then repeat the process by disregarding your x0, which was 3, substituting your x1 to x0, which is your 4 now, would be x0, and then your calculated x2, which is 4.6 now, is placed as your x1, replacing your previous value 4. Hence, on the next iteration, you'd end up with this initial value x0 equal to 4 with a function of -6 and x1 equal to 4.6 with a function equivalent to 7.296. Solving then for x2 gives us this solution, which eventually gives us 4.2708. Computing then for the absolute error now gives us 0.3292, which eventually shows us that we need to repeat the process and disregard x0 again. Substitute your 4.6 x1 to x0 and substitute your calculated 4.2708 to x1. So on the third iteration, your x1 now is 4.6 with a function of 7.296, while your x1 4.2708 will now have a function equal to -0.7899 with this solution. Hence, your x2 now would have this solution based from our initial values, giving us an x2 equal to 4.3029 and an absolute error this time equal to 0.0321. We then continue on the process, disregarding our x0, substituting 4.2708 to x0 and 4.3029 to x1. Hence, on the fourth iteration, your x0 now is 4.2708 with a function value of -0.7899, and your x1 is 4.3029 with a function value having this solution and a value equal to -0.0899. Substituting these values to your iterative solution then gives you 4.3070. And this time the absolute error is 0.0041. Hence, we repeat the process again, disregarding your x0, substituting your 4.309 x1 to x0, and your calculated 4.3070 to your x1. Thus, on the fifth iteration, you'd now end up with an XO value of 4.3029 with a function of negative 0.0899 and an x1 of 4.307 with a function solution like this and a value of 0.0019. Thus, your root value can now be computed like this with a value of 4.3069 based from the solution. Hence, our absolute error now satisfies our terminating condition, which is a value of 0.0001. Thus, we terminate the process. The solution can be tabulated using this corresponding table with a column provided for your important values like x0, x1, x2, fx0, fx1, and fx2, which are all needed on your iterative solution. Here, I also included a column for your absolute error, starting from the second iteration down to the last iteration. This ends the module.